and we take those to be those 200 and 300 level courses that are non-design and non-lab courses. We actually asked one of our undergrad students what she would call those courses, and she paused for a second and then said hell. But we'll go with engineering science courses for this presentation. So in this presentation, we'll start by talking about our interest in engineering science, which comes from our own experience as engineering students and engineering educators. And then we'll talk about a conceptual model of research questions that I've been putting together just to help me think through this space of engineering science courses and what do we have to decide about them when we think about how to teach and how to study them. Then we'll talk about two current studies. One is actually a part of the Flexible Classroom Research Project. We're investigating a particular teaching strategy called responsive teaching during question-initiated dialogue in class. And then we'll talk about a study in my class where we're giving students open-ended mathematical modeling problems and just as studying how students handle those. And then we'll end with conclusions as presentations tend to do. So as Cindy said, I do have a bachelor's degree from here at Michigan. And then I went to do my PhD in aeroastro at MIT. And at the end of my PhD, I knew I wanted to do something with teaching, and I wanted teaching to be a large part of my career. And through some connections, I got connected up with the Tufts University Center for Engineering Education and Outreach. And I did my first postdoc there more for curriculum design, but that's when I discovered engineering education research as a field. And I said, this is exactly what I want to do with my career. So I spent a year and a half at Tufts, and then I had the opportunity to come back here to Michigan and postdoc with Cindy. So I have been back here at Michigan for the past 2 years. So when I was an undergrad here, I really didn't like to design things. I didn't like to make things or build things. I don't really know why. It just wasn't what I was interested in for some reason. I joined the human-powered submarine team. That's what this is a picture of. So I was on the team because I thought I should put something like that on my resume, but I pretty much just wrote the blog from our competition. I didn't really make stuff. And I wasn't seeking out those opportunities. And in the curriculum, they didn't force me to have a lot of those experiences as well. And that was fine with me. Instead, what I liked were these sort of closed-ended, I guess, textbook problems, for lack of a better word, where you take the formula that's taught to you in lecture or in a book and apply it to a problem. Maybe it's a challenging problem, but at the end, you get that right answer. That's just what I like doing. And it worked out pretty well for me here as I was an undergrad. I did very well in my education. I won the departmental award as a senior, so it worked out really well. But as I got older and got a bit more distance from my undergrad education and got more into engineering education research, I realized that a large part of my success was the intersection of my epistemology and the pedagogy that was used in my undergrad curriculum. So the way that I thought about learning was very much these textbook problems, and that's what a lot of my education focused on. That was the primary pedagogy used. So there was a great match between what I wanted and what was given to me, and that was a large part of my success. I began to realize that that wasn't the case for every student. So my wife was actually an undergrad here at Michigan with me in aerospace engineering, but she really wanted to make things. She really wanted to build things, and the curriculum wasn't giving her those opportunities. So literally 2 weeks before we started dating, she transferred to mechanical engineering, and she has her bachelor's degree in mechanical engineering from here at Michigan. And that took her an extra year, but she was much happier because she got to make things. Also, when I was at Tufts, I read this paper called The Marginalized Identities of Sense Makers. That was a really formative paper in my development as an engineering education researcher. So it's from a group out of Maryland that does outstanding work, in my opinion. It's an epistemological N-of-1 study of this guy named Michael, the student named Michael. He was a high-achieving engineering student, but he actually considered leaving engineering because his identity was intertwined with sense-making. So he really wanted to understand why. Not just being able to get the right answer, but being able to understand, why do we use this particular equation? Why does this equation apply? What does it really mean for something to operate in this way? So that's what he was like, but the messages that he got from his peers, from the faculty, from the curriculum, really conflicted with that. His engineering education did not encourage sense-making. It was much more focused on the plug and chug, getting the final answer. Part of the power of this paper is Michael's words in the paper. I really encourage you to read it. It's a great paper. But he drew this diagram that the authors reproduce. So in this diagram, Michael graphs your grades versus your level of understanding. And if you just know how to use discrete Fourier transform as an example, if you could just use them and get the right answer, you get a certain grade. But if you really understand why they work, which is a great increase in your level of understanding, your grade goes up, but not in proportion to the amount of extra material or the amount of extra conceptual understanding that you have. So this was how he was feeling, sort of in conflict with his engineering education. So I read this paper and I was like, oh, I am not Michael at all. I'm like the complete opposite of him. So that's why it was really interesting to read this paper and see what he thought about an education that was similar to mine, but I really liked mine. The authors then argue that there's a need to consider students' epistemologies in retention research. So we study retention in engineering based on a number of facets of students' identities. They say, well, we should also think about whether or not these students want to sense make, or whether they want to build that conceptual understanding. So I was thinking a lot about this when I was at Tufts and started to come to Michigan. And then in October of 2016, I was actually driving Jess from Erie to the Cleveland airport after the Frontiers in Engineering conference. We were talking about this and we discovered, we had a shared interest in engineering science courses. And as it turns out, Jess also read this paper and liked it, but for very different reasons than I did.
So when I read that paper, I thought Michael was articulating exactly all these feelings that I had when I was an undergraduate. And so I really enjoyed that paper and thought it did a really good job of kind of explaining part of my experience. So when I was an undergraduate at Northwestern, I, the opposite of Erin, loved design courses and I loved building things. And so I actually chose my major as mechanical engineering because what I liked to do was think about human problems and then go through the engineering design process to design and build a solution. And that's what I really liked doing. And I chose as many of those kinds of courses as I possibly could when we were allowed to pick different kinds of options for to make up our degree. And on the other hand, I was not a fan of the engineering science courses. And despite that fact, I went to a lot of every single class I could. I made sure I was always attending class. I did my homework with my friends. We discussed things. I went to office hours a lot. But still, I kind of had this sense walking into exam and as I was experiencing these courses that I didn't fully understand the conceptual part of this material. And so I had this kind of mismatch between I thought there was a mismatch between the way that these courses were taught in terms of lectures and homework and my learning style. And so when I decided to pursue a career in research and engineering education, I went to Tufts with this thought in mind, that I really wanted to understand why this kind of system of education didn't really work for me and how I can improve these engineering science courses to be better and be more inclusive for learners like me who really thought that design courses and that type of learning was the way to go. And so for my dissertation at Tufts, I ended up studying students doing homework problems in engineering science courses. So these are pictures of my participants right here. They were either in control systems or fluid mechanics courses. And I filmed them as they were doing the homework that was assigned in those courses. And I was trying to first understand how students were talking about concepts as they were doing their homework. So I looked at their discourse specifically for these incidents where they were trying to make sense of the concepts and apply those concepts to these problems. And looking at their discourse, what I ended up finding is they were mostly engaged in this talk oriented at getting the assignment done instead of trying to make sense of the material. And so in those very few instances where I really saw episodes of sense making, they either began with a student who kind of posed a question or made a bid to have a discussion about it to the rest of the students in the homework group, or there was one instance where this disagreement about an answer that one of the students got started this really long sense-making conversation. And so after I videotaped them doing their homework and kind of analyzed those sessions, I went back to the students to interview them and really ask them, what were your goals during that homework session? And part of that interview process, they also really told me what they valued and things that they thought that helped them really learn engineering. And one of those that we were very surprised by was that they valued discussion and oral explanation, that they really valued talking about these ideas with their peers or explaining it to someone. And that was a really good tool for them to learn. And I think this was surprising to us because that's not how the courses at Tufts were structured at all. They were really mostly lecture-based. But the students knew that this was a really valuable practice. The other thing that really came across in these interviews is students wanted more connections between their coursework and the real world. So in order to kind of build upon the knowledge they already had about the real world, or they knew they wanted to see more of these connections in order to help them be a professional engineer and help them kind of start that trajectory of their career.
So after I'd been back at Michigan for a year, I had the opportunity to teach an engineering science course, one that I had taken as an undergrad. It's Aero 215, which is a sophomore level structures course. And the first semester I taught that course, I was relearning the material a week ahead of the students and trying to make it not appear like I was relearning the material a week ahead of the students. I do kind of know what I'm doing now. A little bit more. But so once I got through that semester, I was able to make better connections between the material in that semester. And at the end of my first year, I felt that I was pretty good at teaching the math. We were doing a lot of active learning. I was really emphasizing the problem-solving process. And I think the students really liked the course, and they liked the way that I was teaching. Over the summer of 2018, though, I started to think, well, I'm pretty good at teaching the math in the course, but it's not a math course. It's an engineering course. So I started to think about, well, what makes my course an engineering course and not a math course, an applied math course or a physics course? So I did some reading, I thought about this, and through reading some papers that we'll talk about later, I came to the conclusion that really what the engineering is this idea of mathematical modeling. So writing or understanding equations that describe natural phenomena with certain simplifying assumptions. And in my 200 level course, we have a lot of simplifying assumptions. And then in the 300 level course, you remove some of those, so on and so forth until you're doing structures in grad school. So I started emphasizing this. I also designed open-ended problems to get students practice with this mathematical modeling. We've continued that last semester and this semester, refining these open-ended problems. So now I want to present this conceptual model of research questions. As I said, this isn't something that's been published or vetted in the literature, just something that I've been putting together to help me think through the space of engineering science courses and what types of questions do people ask or can we ask. So as we said, engineering science courses are these 200 and 300 level courses, but really we see their purpose as covering a particular domain of knowledge in a way that encourages students to make sense of the relationship between the engineering and the science. And we see the engineering as these canonical, so they're sort of accepted in the literature, that's what's in your textbook, these canonical mathematical models that have assumptions and that you can apply to actually design something in the physical world. But also understanding the science, the underlying physical phenomena. So in my course, students have to be able to calculate the stress in a beam. They also have to understand that, well, we can calculate the stress in this beam that's loaded in one dimension, but we can't calculate the stress in a beam that's loaded in 2 dimensions yet. And they also have to understand, what does it mean that a beam has stress? So it's the intersection between the engineering and the science. We call this the sense making. So you'll hear us talk about sense making. This is what we see as sense making, specifically in engineering science courses. We feel that engineering science courses are less studied than design. Design is really uniquely engineering. It's what makes engineering engineering. So it's pretty clear that that's engineering. But engineering science courses also have these relationships with math and science. So the boundaries are a bit fuzzier. So despite the fact that these courses are studied less, they're really important and they're a large part of the education. So this is actually from Jess's dissertation. It's the courses that a Tufts student needed to graduate with a BS in mechanical engineering. There are 10 engineering science courses, most of which, I think all of which we have here at Michigan, and they had 4 design courses. We also see this in the Aero program here. Students have to take 32% of the credits they take are aerospace science, and about 16% are design and lab courses together. So these courses are a large part of our education. So as we said, there are really 2 questions that I see you can ask about engineering science courses that give us the title of the talk. What is the engineering in these courses? What's the content? And then how do we engage students in that content? So the content, the first part is that science. So we have this question of what science content do students need to learn to prepare them for other engineering science courses, senior design, student project teams, or professional practice. And I think this is something that's talked about in sort of every department individually. Every department has courses that they teach. So someone has decided what is important. But I think there's less of a sort of conversation in the field about, in the EER field about what is important in a particular discipline. We do have concept inventories, and if you're not familiar with these, they are multiple choice tests for specific fields. So this is comes from the statics concept inventory, and statics is something that my course covers. So they get together a bunch of experts in statics and say, what should students know in statics? And it's things like Newton's third law, generally good to know, equilibrium, stuff about friction force. So they make this list, and then they make multiple choice questions that get at these concepts. And often many of the wrong answers will follow common misconceptions or errors that students may make. So they have these concept inventories for particular topics like statics or dynamics, but not for a particular discipline like aerospace engineering. ABET does have program criteria, but it's pretty high level. It says aeronautical engineering has to include aerodynamics, structures, propulsion, mechanics, but that's pretty much the end of it, and they leave it up to the department. So this is definitely something that's thought about, but I think it's more at a local level. The next question is, well, part of the content is what engineering practices do students need to learn? And the intersection, the relationship between the two, which is that sense making. These practices might include professional skills or the engineering design process. These are certainly covered in design courses, but there's an open question of, do these skills, should they be taught in engineering science courses as well? And if they should be, what does that look like? What place do these have in engineering science courses? Another practice that we really see as a core of engineering science courses is mathematical modeling. So I was really inspired last summer by a paper written by Julie Gainsbourg out of Cal State Northridge, where she looked at practicing structural engineers as they were designing and analyzing real-world structures. And she looked at how these engineers used math, how they mathematized a real structure or design in order to analyze it. And she found 8 categories of engineering judgment. And a number of these are a basis for the study that we do in my class. So we'll talk about this a little bit later. But this image here is an engineer doing just that, taking a piece of a structure and starting to mathematize it so he or she can actually analyze it. And then problem solving. How do students take a problem with a certain with certain information given? How do they take that problem statement and chart a solution path to the final answer?
So now that Aaron talked about the content, what is the engineering science in those courses, I'm going to talk about how do we engage students in the learning and the doing of this. And so the first and most obvious answer to that is in a course. And in a course, it's usually dominated by thinking about teaching practices. And so when I conducted my dissertation research, I interviewed the students about kind of their experience in engineering as a follow-up to these homework sessions. And one of the things that they started doing was having these short little narratives about some really positive experiences that they had had in a way that a professor taught or a kind of assignment they had. And so these are the teaching practices that they highlighted being really productive for their learning in these courses. So practicing or making visible a problem-solving strategy, asking open-ended questions to all the students as they're going through an example on the board and basing the next step on the student responses, modeling different scenarios and showing how a fundamental equation can be used to analyze those. And again, they talked really about how those real-world examples to the material were really helpful for them. The other way in a course that we can think about this is the assignment design. And that's what I, of course, based most of my dissertation off of. And assignments that they thought that were really helpful for them were intentionally chosen textbook problems. So if they were getting a homework problem that they knew that they were learning procedural knowledge or math, they thought those were really helpful for their learning. But they also wanted more ill-structured problems where they had to kind of figure out a scenario and the mathematical model that they were going to use. And they saw these as being really important to help them kind of prepare them for their professional career as an engineer. They also liked problems where they had to use conceptual knowledge to determine what models that they were going to use to solve the problem, and then problems that required them to integrate their different types of knowledges in order to solve them. The other ways that we can think about how to engage students in the learning and the doing of the engineering are across the curriculum. So like Erin was talking about, these are usually kind of conversations more at the local level, but thinking about how what you're learning in statics as a sophomore then is kind of added to as you're taking the junior level statics course, and how the knowledge that you're learning in both of those courses are going to help students solve their senior design problem. Also thinking about how this is integrated with co-curricular activities. So one thing that we're very interested in thinking about is how are students engaged in these design teams like the Human Powered Submarine Project, and how is that helping them really build their knowledge? Because we know that students have talked about how they see these product teams as really important for them to be able to land an internship or a future job. And so looking at both of these questions, the what and the how, we think it's really important to study the what and the how together. And so the rest of our talk is going to be going over 2 different examples in which we're doing this. So the first one is looking at teaching practices. And so in this flexible classroom project, we're specifically looking at the teaching practices of how that's facilitating the sense-making students are doing in terms of science content and kind of those engineering practices. And so that project, we're specifically looking at the question-initiated dialogue and the responsive teaching by those instructors. The second project, as Erin said, we'll be talking about is assignment design and thinking about how students are really constructing mathematical models while they're solving these homework problems. And we designed some open-ended mathematical modeling problems for students to kind of practice that.
So we'll begin by talking about that first study in which we investigate this particular teaching practice called responsive teaching in class during question-initiated dialogue. Sorry, I have to acknowledge the people that helped us write this paper. So Max Blackburn was an undergrad in EECS, but he's since graduated, and Cindy Finelli, who is our advisor and PI on this project. This part of the project is also funded by the National Science Foundation as part of a larger study on flexible classrooms. So flexible classrooms are a set of classrooms that they've been renovating here at Michigan. I think we have 10, maybe a dozen here at Michigan now in the College of Engineering. These classrooms have a number of affordances that support active learning. So they have movable whiteboards, they have wall-mounted monitors that students can connect to or the instructor can connect to. They also have movable furniture that can be rearranged into front-facing rows or into small tables where students sit in groups of 6. So in this overarching project, we're studying the pedagogy that faculty use in these flexible classrooms, and this includes responsive teaching as one pedagogy, how faculty use the affordances in flexible classrooms, and then also what students think of learning activities when they're doing them in these flexible classrooms. But right now, we're going to focus on the responsive teaching. And I've said responsive teaching a number of times. We should probably define what it is. It's a particular type of formative assessment, essentially. So it's an instructional approach in which teachers elicit student thinking about a particular topic, notice and interpret the disciplinary substance, and then respond in real time to support those disciplinary behaviors. I didn't name this. Responsive teaching is a thing that comes from math and science education. So you can sort of think of it as capital R, capital T, responsive teaching. It is different than just being, I guess, lowercase r, responsive to what your students say. There's a particular focus on the disciplinary substance. So it's really trying to elicit and respond to that disciplinary substance. As I said, responsive teaching has been studied a lot in math and physics ed, particularly. But less so in engineering education. So when we started to look at responsive teaching in engineering science courses, we first had to ask ourselves, well, what is the disciplinary substance? And that's where our definition of engineering science as the sense-making between the engineering and the science comes in. So this is what one thing that instructors can elicit and respond to.
Wait.
Cindy and I wrote a paper for ASE. Oh, yeah.
So can you give an example
Of responsive teaching?
in engineering?
So like an example, let me contrast it with like just being responsive. So like if a student said, I don't understand how you got that answer, and you just like repeat what you said, right? That would just be an example of being responsive. But if they said, I don't get why you got that answer, but you like probe deeply and say like, why don't you understand? What aspects of it, of this, the equation do you not understand? So really getting at a deeper level like that would be responsive teaching. So Cindy and I, as I said, wrote a paper for ASCE 2 years ago where we looked at how instructors can possibly enact responsive teaching during class. And we found that question-initiated dialogue was an opportunity for this. So when the instructor asks a question and the students answer, or when the students ask a question of the instructor. So we wanted to further study responsive teaching in question-initiated dialogue. So our first aim was to create this methodology, to develop a coding scheme that captures students' sense-making in question-initiated dialogue. So we're really looking at when students have an opportunity to engage in the disciplinary practices, which is sense-making. So how are the instructors or students asking questions that allows them to make connections between the mathematical models and sort of the underlying physical phenomena? So we've developed this coding scheme. We'll be talking about it today, and we have a paper on it at ASCE. Our next step, which we've done for pilot results, is to apply this coding scheme to investigate what does this look like in engineering science courses. How much are students asking and answering questions? And then what is the content of those questions or those answers? How much sense making are they doing? And then looking at the ways in which instructors are eliciting students' ideas in pursuit of sense making. So how are instructors engaging in responsive teaching? And then we want to develop evidence-based techniques for instructors to enact responsive teaching. So we'll focus on the methodology. So we have developed a coding scheme called the Teacher Eliciting, Noticing, and Responding Protocol, the Tenor Protocol, which is coincidentally the instrument I played when I was in marching band here. Weird how that worked out. So the Tenor Protocol has 5 categories. There are 24 subcategories. I won't go through them all. I want to focus on the sense-making categories. That really relates to the disciplinary substance. Instructor or a student can ask or answer a question. They can invite or offer a number or definition. So an example might be, what's the stress when you're solving a problem and you're doing the math and then the instructor says, what's the final answer? What's the stress? And the answer is something like 5 kilopascals. Somebody can also ask or answer about the mathematical reasoning or process. So just saying, the instructor might say, how did you find the stress? And the student would say, I use Newton's third law. So just at a level like that. Then the instructor or the student could give scientific or engineering reasoning with respect to an example. So if we're talking about this example where they're calculating stress about a beam, the instructor might say, well, you did Newton's third law and you have to, you said this system was in equilibrium. Why is this system in equilibrium? So getting at the underlying reasons of why we can apply a certain equation to this particular example. Or somebody could talk about scientific or engineering reasoning just in general. So the instructor or a student might ask, when are real-world systems not in equilibrium? Can we actually analyze a system like this? Those are, I think, scary questions to get as an instructor, but they're also great questions when you see that the students are really thinking about, well, how does this apply to the real world? So as you can see by the way we've arranged this, we see that generally we think that sort of the 2 categories, when you're talking about numbers or definition or mathematical reasoning or process, there's not engineering science sense-making happening. But when you're talking about that scientific or engineering reasoning, then you are having engineering science sense-making. There are likely some edge cases on the border, and that's a task that we're going to be going through and identifying this summer. Oh, sorry.
Okay.
You do.
So as Aaron said, we have some preliminary results from kind of fine-tuning this protocol. And so in order to do that, we chose 2 courses that we really saw to be different when we were looking at the data that we had. So the first of these courses was a 400 level course that had about 60 students enrolled. And the room was arranged like this with front-facing desks, and all the students were sitting there. And the primary activity of this class was the instructor delivering content to the students. In contrast, the other kind of data that we looked at was in course 2 was an intentional small section here at the University of Michigan that had 25 students, and that the desks were arranged in pods that had 4 to 6 students at each of these pods. And so the primary way that class was kind of delivered there was this discussion. So the professor would ask questions of the students. Sometimes the students would talk to each other. The students would ask. So it was like this ongoing discussion. And so we saw these to be very different kinds of courses. Our coding of this was not rigorous or scientific analysis, but we're planning on doing that soon. And so the initial results we have from that are specifically looking at the instructor utterances. So in terms of the questions that they asked of the students, there were a majority of those questions were non-sense-making types of questions. But if you look at the way that they responded to the students, so their answers, there was in course 1 about 25% maybe of sense-making responses, but in course 2, there was over 50%. And if we look explicitly at the student utterances, so the questions they asked of the professors, again, were mostly non-sense-making types of questions, but the responses that they gave to the instructor questions were about 25% in course 1, and again, over 50% in course 2. And
Yes.
so,
Can you go back to the slide for just a
Yep.
second, please? You gave us this caveat at the bottom of the last slide. This is neither scientific nor rigorous. This actually looks pretty cool. What part of it am I supposed to put a caveat on?
I also think we repeated the graph twice.
Because they do look similar, don't they?
Yeah. I'm gonna claim that I have a 3-month-old child, so blame me. I don't sleep a lot.
But what part? I mean, this seems reasonable to study the utterances. I mean,
Right.
what are you uncomfortable with in the method that we should be?
Yes. So we haven't calculated inter-rater reliability.
Okay.
We haven't looked at a lot of classes. We haven't fully discussed edge cases.
Yeah, but you just study one class. It's okay.
Yeah. I mean, so yeah, I wouldn't say let's use this data to make generalizable claims about engineering science courses. We intend this to be, or I wouldn't claim. Yeah, I mean, I think we just need to do a better job of rigorously analyzing and checking the coding that we apply.
Cool. Thank you.
So we were using this to kind of demonstrate how we wanted this to work in kind of a test case. But going forward, so we here with our preliminary data are trying to show that the Tenet protocol identifies the differences in courses between the amount of student sense-making and the instructor responsiveness. But we are hoping to do a more rigorous application of this on 27 lecture videos that we have that were taught by 11 instructors that we have for the fall. And then from there, kind of develop these evidence-based techniques for instructors and developing some professional development. So the second study that we're going to be talking about today is about the open-ended mathematical modeling problems that we are designing and then studying in Aaron's Aero 215 course. And we did this work with Tim Chambers in the Material Science Department and Laura Hirschfield in the Chemical Engineering Department.
So my motivation for putting these open-ended mathematical modeling problems into my course was really my desire to create a better course. I wanted the course to be more about mathematical modeling, and so I had to put that in somehow. So I designed these problems to incorporate and allow students to start building engineering judgment in the course. So I admit that I'm never going to get them to practicing engineering judgment at the end of my course, or even at the end of your undergrad here at Michigan. But I wanted to start them doing things that would be productive beginnings of engineering judgment. I also wanted to reinforce the mathematical modeling aspects of class. I had also had sort of a long-standing belief that I should be connecting the material to real-world situations more, and I tried a number of ways to do this. I had student project teams come and present, but students saw those as more just recruitment tools. I had grad students come and talk about their research, and sometimes that worked really well, and sometimes that was a bit too dense for the students and myself. So I saw these open-ended problems as another way to connect the course to the real world. I did a midterm student feedback session with Gren, actually. She found that students wanted more connections between the material and real life. So students said things like, provide more real life examples or demos. We would like to apply the concepts to real world problems, or give us field trips. And I was like, yeah, that's great. I'd love to go on field trips. These are all great ideas. The challenge then is getting these into your course. And open-ended modeling problems are one way that I went about this.
So my motivation to designing and then studying these problems is I really wanted to build off my dissertation research. So as soon as I kind of finished that study, I really wanted to start designing new problems based on those results. And one of the things I'm really intent on doing is trying to design homework problems where students aren't kind of task producing or really trying to get that one single final solution, but really focused on the process and thinking about the concepts. And these open-ended problems, I think, are a really great way to do that. I also wanted to incorporate some of these things that the students told me that they really wanted, which was more ill-structured problems and also more links between the work that they were doing in class and the problems they were asked to be solving and kind of the real world. So as we were talking about before, our theoretical basis to this study is Julie Gainsbourg's work. So she followed around construction engineers at 2 different firms and was watching how they mathematized these structures to analyze them or analyze the design. And so as she was doing this, found 8 different ways that these engineers displayed engineering judgment in their work. And 5 of these mapped really well to the work that the students are and did do in Aaron's Aero 215 course. So the research questions we had going into this project was first, how do students evaluate their mathematical model and their final answers? So how are they kind of starting the beginnings of engineering judgment? But first we wanted to look at how students are charting a solution path and solving these open-ended modeling problems.
So this is what the first open-ended problem looked like last semester. So I told students that a wealthy donor wanted to build a bridge between the FXB and the GFL. And so I gave them this model of a bridge with a nice observation platform where people could look out over the wave field. If you have ever seen a bridge in your life, you know that this is a really bad design because the bridge doesn't actually touch the FXB. It's just supported by 2 cables. I wouldn't go on this bridge. But this was, I think, like the 3rd, 4th week of the semester, so we can only analyze simple structures like this. So I first asked students to estimate the loads on a bridge. So they had to think about, well, how many people might use this bridge? What does a person weigh? Is there going to be snow on the bridge? Probably. Well, how much does snow weigh? So they had to estimate loads and make a mathematical model of the loads on a bridge. And then once they had that, I had many different solutions to that first part. It was truly open-ended. Students then had to take their model and plug and chug and calculate the tension in the cable. And then once they had the tension, they could calculate the stress and size the cable, pick a material and a diameter that would give you a certain safety factor so that the cable wouldn't break. So they were sizing the cable for sort of the worst case load, which they had modeled in part 1. Then students had to discuss a more accurate model, which wasn't hard to do with this one. They also had to name other real-world factors that an engineer might actually consider if they were designing this bridge. They had to size their cables for strength, but they also talked about how real engineers might consider corrosion resistance or manufacturability or cost or even aesthetics. So then the second problem was given at the end of the semester. We had just learned beam bending, so we could make a better model of a bridge. It actually touched the FXB this time, so that was nice. We put a column in the middle. So this is a different model. If you know anything about statics, the last one was statically determinate. Easier to solve. This one is what's called statically indeterminate. But I gave students a load for this bridge. So I estimated how many people would be on this bridge and gave them a load. But the beam, we were analyzing a beam of this bridge. I also said the weight of the beam also was a self-weight and influenced the bending moment. So students had to go through and calculate the bending moment based on this load that I gave them. That was a closed-ended problem. There was one correct answer. But then once students had that, they had to select a material and a geometry for the beam. Once again, that would give you a certain safety factor. The interesting thing is that when you select a material and a geometry, it influences the weight of your beam, which is part of the load, which influences your bending moment, which influences your stress, which also the weight of the beam influences the cost of the beam. So they were now considering cost, and there's a lot of interdependencies that students had to calculate. So they were selecting a material and a geometry. We actually had a contest. We tried to see who could find the lowest cost beam that still had a certain safety factor. So I thought that was fun. I think some students did as well. Once they had their beam, they had to, once again, sort of plug and chug and calculate the maximum deflection, also calculate the total cost of that beam. And finally, as with the first problem, they had to discuss a more accurate model.
So the way that we studied this was both quantitative and qualitative. And so when we started giving students these problems, we kind of had this fear that students would react poorly to them because of the open-endedness. They might have some effect on their grade, or that they would be kind of long or tedious to do. And so we wanted to collect some data about how the whole class felt about these problems. So we gave the students a survey to gather that type of information. But since we designed these in really thinking about trying to change the way that students are doing homework and their process of thinking about them, I conducted interviews with 5 of the students. They were all male aerospace sophomore engineering students. And I started the interviews by asking them first, how did you create your mathematical model? How did you chart a solution path? And then I asked them in the interview to evaluate their models. So I asked them, why is your model the best model? Why is it the best approximation of reality? And had them evaluate that right there in the interview. And so today I only have time to present part of our results, but we're just going to look at the solution path and the evaluation of open-ended modeling problem 2. So what we saw in this problem that was the biggest difference between all these students was their choice to either write a computer program to optimize finding the solutions or doing it all by hand. And so you can see here that Oliver, who's on this side, optimize the whole thing, but the one thing that he didn't do was he just decided that I-beam was the beam way to go because he knew from living in the world that I-beams were the best kind of beam. So we saw some differences in the choices that students made here. In thinking about the evaluation, the thing we noticed first and foremost was the frame that students were talking about this in. So in evaluating their beam as good or bad. So they would start kind of answering my questions by indicating if they were answering this question and they were thinking about it in terms of the course, or they were thinking about it in terms of the real world. So you can see here, Harry and Oliver are talking about how they thought that they really had a good model because they used MATLAB to test lots of different beams. But Broderick, in contrast, is saying that he thought that his model was kind of poor because he knows he could have used a computer program to kind of optimize this situation and get a better answer. In terms of the real world, we saw the students really talking about the amount of knowledge they had in the model. So they recognized that in comparison to this first problem, that the second design of the bridge was so much better, but they also told me that they knew that they were going to take another statics course going forward and that they were going to learn more, and therefore this model was too simplified and they would learn how to make better models over the course of their engineering education. So in terms of the survey results, 36 students chose to take the survey, and most students said that they enjoyed solving these open-ended problems. Not as many, but quite still a number of students said that they liked these open-ended problems more than typical homework problems. The students also, many of them agreed that they wanted more open-ended problems in this course or their other engineering science courses. And then we also asked the students if they were using mathematical models, something that had really been Aaron's goal, and all but one student said that they had perceived using mathematical models. So in the interviews, we asked the students how they like these problems as well. And the first 2 things we found weren't really that surprising to us. That, again, they really liked that these problems related to the real world, and it made them feel like they were really doing engineering work. They also identified that they said, yeah, I think these problems really helped me learn the course material. So we took that as a positive. That was good. One of the things that surprised us is the students told them they were fun. And we didn't have just one student say this, but multiple students said, hey, these were really fun. So Henry said, when I was sitting down doing this one on MATLAB, I kind of said to myself, this one is actually kind of fun. It didn't really feel like grinding some problems. And then students also reported and they said, oh, these problems really made me think. And so what we saw is some of the students were comparing them to their plug and chug problems that they usually did for homework. So Henry here says, this requires thought. You know what I mean? It requires thought, explanation. You know, like I had to logically kind of deduce where I thought the maximum bending moment would be. So here we saw in mapping back to Julie Gainsbourg's work that students were really making these decisions and judging where technology would really help them in solving the problem. They used real world experiences to make decisions. So one of the students told me about how the way that he decided about to load the bridge with snow was because he grew up in Michigan and he knew that. So determining what elements and conditions are typical, or they used kind of their knowledge about the real world to justify that their calculation had a good answer, so that the dimensions of an I-beam were good because I know what an I-beam looks in real life. And then we also saw them recognize the limitations of the models. So students talked about how they really had to simplify and eliminate things like wind because they didn't quite know how to incorporate that into their model.
So I'm teaching this course again this semester, and we are doing these open-ended mathematical modeling problems again, but I've made some modifications. So first is, instead of a bridge, we're actually doing an aerospace scenario now. So we're modeling the Nomad, which is an airplane in the lobby of the FXB, the aerospace building. And so it's really cool to have students modeling something that's literally sitting outside of our classroom. In the first open-ended problem, they were sizing the landing gear, so they had to determine how this airplane would be loaded in sort of a worst-case scenario. So what's the lift? What's the drag? Students were also putting the airplane in dynamic situations, such as a hard landing. Then they had to turn that acceleration into a fictitious force and put that into their calculations. The second open-ended modeling problem, students are literally doing it right now, maybe literally this very second. It's due on Friday, and we have so they have to turn that in. It's similar to the first one, where there is a wing spar beam, the main structural member of a wing, loaded with a lift force that I've given them. I calculated based on the real airplane specs. And the weight of the beam is also a load on that beam. So they have to, once again, size the wing spar beam and choose a material and a geometry and plug that into their equations. And once again, we're trying to find the lowest cost beam that has a certain safety factor. The other thing we're doing is post-assignment discussions in small groups. So Jess was asking students to evaluate their models, which was great, but it was only 5 of our 47 students had the opportunity to do that. And self-assessment is an important component of teaching mathematical modeling. So I really wanted all students to do that. So now students turn in their problems at the beginning of class on Friday, and then they have a discussion with other students about what they did and how it compares with their peers. And then we have a large group discussion. This is us having class in front of the Nomad. So we went out and talked about how everyone modeled the airplane. So students wanted field trips, they got field trips. Granted, it was 20 feet outside of our classroom door, but baby steps. So this is an enormous model that is a work in progress, not vetted in the literature, and certainly not comprehensive. Just a way for us to think about what do we need to consider when we're teaching or putting together engineering science courses. And it's been helpful to think about all of these different aspects and bring them together. As I said, all of this has been, I think, studied before in some silos, right? I mean, people have certainly researched teaching practices or assessment design before. But we think there's a lot of value into putting it into the larger context and addressing, well, what should we be teaching? And once we know that, how are we teaching? And we have taken some ideas about mathematical modeling and sense making from the literature, and we're investigating teaching practices and assignment design that get at that. So we're really hoping to do more of this work in the future and really dig into some of these other questions. It's certainly a large problem space, but really excited about it, both going into sort of more of the engagement side, but also going and looking at the content that we should be teaching. We have a bunch of ASEE papers. We have given you the 30,000 foot view of our work. If you want to learn more, we can send you our ASEE papers in 19 days when they're finally finished. They're almost there, I swear. But so we'd be happy to send you our papers, or if you want to talk to us, come to ASEE. If you're there, we welcome you at our presentation. We plan to continue the work onto this in your future. We welcome your ideas, thoughts, opinions, assistance, courses to study, whatever you can offer. Next fall, I actually won't be at Michigan anymore. I will be an instructor at the University of Colorado Boulder. Spending a lot of time in those mountains, hopefully. I'll be an instructor in aerospace engineering, but the department's really interested in engineering education research and some of these questions. So I plan to continue this work. Jess is still currently looking for a position, but she's also really interested in continuing this. So looking at somewhere where she can make that happen. Finally, we have to thank everyone that helped with this. So Cindy Finelli, our advisor for letting us do this and also advising us. Max Blackburn and Candace Wywell, who are undergraduate students who've worked with us. Jessica Hernandez, who's a master's student in the School of Education. And Tim Chambers and Laura Hirschfield for their help on the study of my class. And thank you to our many participants, students and instructors, because there's a lot of people behind the data in this project. So I see we went over Michigan time by 5 minutes. I don't know if we have time for questions now. Maybe we can take a few now. We'll also be around for the social hour if you want to ask us more questions. All right, Michael.
Yeah, hi. So one of my bigger questions is, how do you measure the effectiveness of open-ended problems on how it's integrating students in the engineering process? Like, do you just measure it by the score that they receive, and also how do you assign the score that they receive? But also, do you measure it by improvement from open-ended problem 1 to open-ended problem 2, or? Yeah,
so that's a really great question, right? How do you assess learning as a result of these? We have essentially chosen to not address that right now, right? We're just trying to get a handle of how do students attack these? I mean, and our reviewers gave us this. They're like, I want to see what scores students got on these, right? And or like, do they do better on the exam after doing these problems? I mean, I think there's a lot of mitigating factors, and right, like we're trying to teach practices of engineering judgment that aren't like, as you know, we don't test on our exams because of the way we have to write exams. So. And also the grading of these open-ended problems, we're really focused on giving experience and grading based on like the procedure rather than like the right answer. So that is a very great question. How do we assess this? I don't know, because I think the things we're trying to teach are really outside of the traditional assessments we have. So that's definitely a question that we will have to address if we want to convince other faculty to use these, right? But we're just ignoring that for right now. And I think there's a lot of interesting stuff about how students attack these problems.
Right, and so I see it as the piece where I'm really looking for that, where it might not turn up in the grade, is in the interviews, right? So I'm trying to understand, like, how are students approaching this? How are they thinking about this process? And really trying to assess of, like, are they thinking about it in the way that we designed to, or are they totally approaching it differently? And we saw that in our data, that we had one student who just said, I'm going to treat this like a normal homework problem and just like get it done. And you're always going to have students like that, but I think we're looking at, is it really making students do the thinking that we kind of are setting out and then want them to do?
So actually, could I also give you my opinion as a student who's doing these open-ended problems?
Sure.
I feel like that it is effective in like integrating the students in the engineering process. So I think it might be a worthwhile endeavor to look into how to evaluate that effectiveness.
No, yeah, definitely. I think too. So as the instructor of your course, another thought, and this is something that I continually think about, is like how, right? It's like, how many doses of a vaccine do we need to do before it matters, right? And it's sort of like, we do, right? You're not doing these in any other classes right now. Yeah. So does that blunt the effectiveness of doing them in 215, or like, do we need to do them in one course per semester? Do we need to do them in every course? You know, this is something I always worry about, like, how do students perceive the way I teach is just, this is how Dr. Johnson teaches versus like, this is how engineering should be. So yeah, I mean, yeah, I feel like, yes, your question is, I'm glad you like them, and I agree. I think that's something we want to think about, the effectiveness.
We should probably wrap up, but I think there's food out there. Grab something to eat and come on in, but if you need to head out, I know people have other obligations, so
yeah,
feel free to do that. So
thank you for coming,
Aaron and Jess.
Yes. Thank you for the opportunity to, or the reason to shower and shave and get out of the house.
How's parenting going now?
It's rough. No, I mean it's good. The 2 kids is a lot more than 1 kid. So
No, yeah.
yeah, no, it's
But I was like,
good.
she
But,
probably just
yeah.
didn't see.
He was, but then he started rolling over, like last week. And when you roll over, you what?
Does that change things?
Yeah, so you can't swaddle them anymore because if they roll over and their arms are swaddled, they can't turn themselves back. So he's sleeping unswaddled in his pack and play now, and so he wakes up like every hour and a half at night, which is brutal.
I mean, yeah, I thought about it like myself, but I've never like talked to
It's
people about it.
it's rough.
Our daughter's